Roller coaster. An empty 900-kilogram roller coaster test vehicle starts from rest at point A, rolls down a frictionless track, goes around a loop, points B and C, and then flies off the incline at point D. The dimensions are capital H is 80 meters, R is 15 meters, lowercase h is 10 meters, and theta equals 30 degrees. So here's point A, B, C, and D. Here's uppercase H, here's lowercase h, and there's theta. A. What is the speed of the test vehicle at point B? B. What is the speed of the test vehicle at point C? And C. What is the speed of the test vehicle at point D? Continuing the question, what force does the loop's surface apply on the test vehicle at point B? Part E. What force does the loop's surface apply on the test vehicle at point C? And F. How far in the horizontal direction from point D will the test vehicle land? A. What is the speed of the test vehicle at point B? Use the Earth test vehicle track system. The gravitational force and normal forces are internal forces within the system. Since the track is frictionless, there are no external forces, so total mechanical energy is conserved within the system. The velocity is the same regardless of the mass of the test vehicle, as shown in the equation above, right here, where mass cancels out. So we set the initial GPE, the initial kinetic energy, and that's all at point A, equal to GPE at point B and the kinetic energy at point B. GPE at point A, mg, uppercase H, it's not moving, so that's 0. Then the GPE at point B is 0, as it's at the bottom, right here, of our reference frame, plus 1/2 mvb squared. Do a little algebra, we get VB is the square root of 2g, capital H, substitute in the variables, and we'll be using 10 meters per second squared for the acceleration, and we get a velocity at B of 40 meters per second. Use conservation of energy again. At point C, there's kinetic energy and GPE. Be careful with the GPE. The height at point C that we need, this height here, is 2r. It's not the given radius of the loop, which is r. That's a common trick people fall for. So this height will be 2r. The energy at all points is the same. So use the GPE at point A as the total mechanical energy. So EA equals EC. That saves us some math. GPE at point A is mgh. Then here's our GPE at point C. And again, notice the 2r plus 1/2 mvc squared. Once again, do a little algebra, substitute in the numbers, and we get the velocity at C is 31.6 meters per second. We're going to make another point here. Here's the equations from the previous slide. Now the difference in GPE between point C and A is transformed into the kinetic energy at point C. Right? So this has a certain amount of GPE. Over here, we have less GPE, and this amount right there is what gets converted into kinetic energy. Use conservation of energy again. And again, we'll start with the energy at point A, and that's GPE of A equals the GPE at point D plus the kinetic energy at point D. And notice over here, we put in mgh, right? That's still the height of there. mg little h, okay? That's the height at point D. Do a little algebra, substitute in the values, and we get 37.4 meters per second, which is faster than the speed at point C. That's because at point D there is KE and GPE again, but the speed of the test vehicle is greater at lower heights above the ground. Less of the total mechanical energy exists in the form of GPE, right? This GPE is less than all the way up here, increasing the total amount available for kinetic energy. What force does the loop's surface apply on the test vehicle at point B? Whenever a question asks about force, the first step is to draw a free body diagram and then apply Newton's second law. At this point, okay, you've got the normal force in the up direction, mg in the down direction. The vehicle is moving in a loop, so use Newton's second law with centripetal motion. Substitute in the velocity of the vehicle that we found in point B for the acceleration, centripetal acceleration, which is v squared over r. Forces that point towards the center are assigned positive values. So our normal force is pointing towards the center, mg is down. So the sum of the forces is normal force minus mg, which equals mv squared over r. So rearrange, the normal force is mg plus mv squared over r. Factor out the m, so you just have to multiply it once. Substitute in our values, and we take the velocity that we found at point B earlier, and the normal force is 1.05 times 10 to the 5th newtons. What force does the loop surface apply on the test vehicle at point C? The vehicle is underneath the track, so both the normal force and the gravitational force point towards the center. So when we sum our forces up, we have a positive value for both. So the normal force now is going to minus mg plus mv squared over r. Once again, factor out the m to make it simpler to do the math. Substitute in our values, and we get 5.09 times 10 to the 4th newtons. How far in the horizontal direction from point D will the test vehicle land? Here's an expanded view of the last pieces of this problem. And what's going to happen when the vehicle leaves the ramp, it is a projectile motion problem, as the only force acting on it is gravity. So it's going to do something like this. Its initial velocity, v0, is 37.4 meters per second from part C. Resolve the velocity into its x and y components. So the x component is v0 cosine theta, the y component v0 sine theta. Substitute in our numbers, and this is what we have for the initial velocity in the x direction and the y direction. Typically, the first thing we do for projectile motion problems is find the time it takes to fall, and that will be in the y direction. So we use v0y, the height, lowercase h of the incline, the acceleration in the y direction is minus g, and the second kinematics equation in the y direction is what we're going to use. Solve the resulting quadratic equation and take the positive root. Keep an extra figure, as this is an interim step in solving for the range, how far it goes. So here we go. Here's our height, here's our v0y, and here's the acceleration, well, half the acceleration, and we get t is equal to 4.214 seconds. We now solve for the range using v0x and t from the previous slide, and the second kinematics equation, this time in the x direction. So here we go. The acceleration in the x direction, 0, and we'll start this right at x0 equals 0. That's going to be right here, and then we're finding what x is. It's 32.4 meters per second times 4.214 seconds, or 136.5 meters. We'll round off the range to 3 significant figures, as this is our final answer.